Yes, I'm ready.
Okay, perfect. Then we can get started. So our last speaker of the day is Bartłomiej Pawlik from the Silesian University of Technology in Poland, and he's going to talk about the nonchalant procedure.
Yes, thank you, Narad. Firstly, I would like to thank the organizers for the opportunity to give this talk, and I will tell about the nonchalant procedure, which is a quite new concept. It was introduced by Gryczuk, Kordulewski, and Niewiadomski 2 years ago, when in one of their papers. And this talk is based on joint work with Jarosław Gryczuk and Hubert Kordulewski. So let me start with some definitions. Let X, Y, and Z be words, and let the U be a word which is a concatenation of X, Y, and Z. And every word X, Y, and Z is called a factor of the word U. And if we concatenate a word with itself, then the concatenation is called a square as a word. A word U is square free if it does not contain a square as a factor. So here we have two examples. The word repetition is not square free because it contains a square TT, while recreation is a square free word. Let me tell you about extension. AB is the word and X is the letter. Then the word AXB, as a concatenation, of course, is called an extension of the word AB. So for example, all the extensions of the word 1, 2 over the alphabet 1 and 2 are 1, 1, 2, 2, 1, 2, 1, 2, 2, and 1, 2, 1. The red ones are square free, which are most interesting for us in this talk. And finally, we say that the square free word is extremal if every of its extensions is not square free. So we have a few extremal words over alphabet 1 and the alphabet 1, 2, which is not surprising because we do not have much square free words over these alphabets. But the classical theorem of Thue says that over the alphabet 1, 2, 3, we have arbitrary long square free words, and we do have some extremal one as well. This is the shortest one, extremal. So if we put any symbol anywhere in this word, it would generate a square. So the Gryczuk, Kordulewski, and Niewiadomski showed that there exists infinitely many extremal square free words over the alphabet 1 to 3 in 2019. And this result was extended by a very nice theorem by Lucas Moll and Narad Rampersad. A few months later, namely they showed all the lengths over the alphabet 1 to 3 for which we get the extremal word. In particular, if we have a length greater or equal to 87, then there is extremal square free word over this alphabet. So the nonchalant procedure is strictly related to the existence of the infinitely many extremal words, and it goes like this. The first element of the sequence is the word 1, and every following element is the square free extension of the previous element by inserting at the rightmost possible position the least possible letter. The procedure was considered over the alphabet 1 to 3 in Gryczuk, Kordulewski, and Niewiadomski paper, and it goes like this. We have, firstly, we have the 1, and then we extend it at the rightmost position by 2, because if we put here a 1, we would generate a square. And then we can put the 1, 3, and so on until we get the Z-min word over the alphabet 1, 2, 3. This word is maximal in the sense that we can't put any symbol at the rightmost position. So the nonchalant procedure has to go deeper in the penultimate position, and we put here a 3 because 1 and 2 would generate a square. And so on and so on, we can generate larger square-free words. So Grudczyk-Ruldewski and Niewiadomski conjectured that the sequence of nonchalant words over the alphabet 1 to 3 is infinite. It says that we can't get any extremal word by generating the following words in this sequence. And the answer is not know if this is true until we don't know the answer yet if this is true. But we have some facts about this procedure. We check that it does not stop in 10,000 iterations. And the deepest entries in this 10,000 iterations is 20, and it was obtained twice. So the procedure had to go 20 position into the word from the right side to put a new symbol. Once there is entry of the length 15, and so we can state that it doesn't go so deep even for the large words. The number of positions of which the nonchalant words are square-free extendable is increasing in such manner that if new maximal value is obtained, then it never goes below n-2. And this is the observation after looking at the 1,000 iterations. And when we get the word of length 1,000, then it were extendable at 75 internal positions. So again, not so much. And we do have some results inspired by the nonchalant procedure, inspired in such way that we try to do the nonchalant procedure in the 4 elements alphabet, which could be naive, because if there are no extremal words over alphabet 1, 2, 3, 4, then this procedure obviously doesn't stop. But as I am aware, it is not known if there are any extremal words over 4 letters alphabet for now. And what we observed, the results were somehow surprising, because we made 50,000 iterations, and the nonchalant procedure put 1 symbol on the penultimate position only 33 times in 50,000 iterations, and in the all other iterations it put the symbol on the rightmost position. So we thought that maybe every word over the 4-letter alphabet, a square-free word, is square-free extendable at the end or at the penultimate position, which is quite a long shot, because we looked only on the nonchalant procedure, but we had to look closely on that, because if that would turn true, then it would prove that there are no extremal words over this alphabet. Needless to say, we found a square-free word over this alphabet, which is extendable neither at the last nor the penultimate position. So another more general result is that for every pair of natural numbers such that k is greater or equal 4, t is less than k, there exists a square-free word over the alphabet 1 to k, which is not extendable in the first 10 internal positions. And our proof is constructive. This statement is somehow surprising as well, because if we take a big alphabet, big enough, I would say 100 elements in the alphabet, and we take a long square free word, then it's mostly extendable at any positions in several ways. So, in particular, over the alphabet with 4 elements, we can construct a word that have length 319 symbols, and it is not extendable at internal first, second, or third position. So the word is long, but I do think so that this is the shortest word of them with such property. Well, if someone will find a shorter word on the alphabet with 4 symbols that is not extendable at first 3 internal positions, then the dinner is on me. On the next time we shall meet in real life, but I believe that there awaits some post-pandemic time when this is possible. I believe that we were recording this, yes?
Okay. Yes.
Okay, so there's no going back with that statement. And more general, if we have alphabet with k elements, then the length of the word is k times 2 to the power of k squared. So these are big words, so we can see. We did think about some modifications of the nonchalant procedure. And the first modification that came up is that the first element is, again, the word 1, and every following element is the square free extensions of the previous element by inserting the least possible letter at the rightmost possible position. So it looks very, very similar, and it acts very similar to the previous classical nonchalant procedure, but it goes differently when we get the word of the length 25, I believe. And so then this original nonchalant procedure in this word puts a 3 2 positions deeper than the rightmost. And this modified procedure puts a 2. Because how does it work? It tries to put 1 somewhere in the word. It can, so it tries to put 2 from the rightmost position, and it can put 2 right here. Original procedure, it tries to put 1 at the end, 2 at the end, 3 at the end. It can't. It tried to put 1, 2, 3 here, and lastly, it tried to put 1, 2, 3 in here, and it's a square free word. So we conjugate that this modified nonchalant procedure never stops as well, but again, we do not have a proof. Maybe these conjectures are equivalent. That would be a nice result too, if someone could show that. We didn't do that for now, and we modified this in several more ways, and we tried to attempt to extend it to translate the nonchalant procedure to the other fields of mathematics. And firstly, we got to the number theory. So it looks like the recreation of mathematics, but as it occurred, there are some deeper results similar to these investigations. So how to translate it to number theory? We say that a prime number p is an extremal prime number if every non-trivial extension of P is a composite number. So again, we are putting a single digit in some positions of the number, and we get every time a composite number. A non-trivial extension means that putting 0 at the leftmost positions is forbidden, because if I put 0 here, then obviously I get a prime, and there's nothing interesting about it. So we found some extremal primes not greater than 10 to the power of 7, and there are 8 of them. Looks like this. And for example, I took this one and putting some random ciphers every time we get the composite number, and it works for putting any cipher anywhere. I just showed you here a few examples because showing all the extensions would took a lot of place. We conjugate that the set of all extremal primes is infinite. So when we thought about this and we did some research, we saw that there is some similar concepts which were investigated by several mathematicians. For example, there is something like digitally delicate primes. And it goes like this, that we have a prime and we replace any of its digit by another digit. And every such replacement will give us a composite number. So the existence of such primes was asked by Murray Klumpkin in 1978. And Paul Erdős showed that there are infinitely many. Klumpkin asked if there is any prime with such property, and Erdős did not show any of these primes, but he just showed that there is infinitely many of them. And later in 2011, Turnstile proved the positive proportion of such primes. So there are relatively a lot of them, as we know. We do know that similar property for composite numbers is proved by Villaseta. So there are infinitely many composites that remain composite after inserting a single digit between any digits or at the ends. And as far as I know, Villaseta and Selfridge, I believe, did ask themselves the same question as our conjecture about primes, but I think that they don't have the answer yet. And similar concepts, it's the minimal primes by Geoffrey Shalit, namely, if we take any prime and we remove some of its digits, then sometimes we get a prime as well. And the set of all primes that can be obtained by removing some digits of a given prime have the minimal element. So Geoffrey Shalit showed in 2001 that the minimal element is one of the primes that are shown here. And I don't know what happened. Okay. So back to our concept, the nonchalant procedure for the primes. We start with the prime number 2, and every following prime number is the non-trivial extensions of the previous prime number by inserting at the rightmost possible positions and the least possible digit. So we started with 2. I can put 0, 1, and 2, or 2 at the end, but I can put 3 and I get a prime 23. Then it occurs that I can put 3 again and again and again. And this number is not extendable at the rightmost position. I can put 0 or 1 on a penultimate position, but I can put a 2, and so on and so on. And me and Jarek Gryczuk, we couldn't get agreement about our intuitions about how this procedure will work. So I divided to the two conjectures. First conjecture by Jarek Gryczuk is that the sequence, the above sequence of nonchalant primes is infinite, and my conjecture states that this sequence is finite. So if we are talking about inserting a primes into inserting a ciphers into a prime and investigating some properties, then it is important to look what happens in another positional systems with other bases. So we checked this this procedure into the bases 2 to 9, and it stops for 2, 3, 4, 5, 7, and 9. For 6 and 8, it didn't stop for that many iterations. And another thing is that I'm not so sure about most of these results, because when I trying to investigate if the 800 digit number is prime, then I can't know for certain. I get the probably prime numbers, which goes for some tests. So maybe it is it is not true. If we talk about this this original sequence, then we have certainty for the first 24 terms, I believe, and the bigger ones are just probably primes, but it seems feasible to work on that. And I think that that's all for now. So thank you.
Oh, thank you very much. Does anyone have any questions?
Okay, may I ask?
Yes. Oh, yeah.
Okay.
Go ahead, Arseny.
Yes. Yeah. So thank you for a very nice talk. Actually, I think that what you said last about using this probabilistic tests for prime numbers.
Yes.
At least this means that when you get finitely many, that it's really finitely many, yes? Because probabilistic test has had only one side error. So you can sometimes get a composite number for a prime, but never you can get a prime for a composite. So at least those results you put for alphabet for these 6 alphabets, they should be true, yes. And you only can be sure about so this bases 5 and 8, I think, but 6 and 8, sorry. And at least the probability of getting wrong is so small if you use any of popular tests, like, I don't know, Miller tests, Solveig-Strassen tests. I think everyone would do, so you can say that you can be sure with very high probability that this go this way. But
Okay.
okay, if you consider this problem, then the more digits you have in your positional system, it's probably you have more degrees of freedom, and it can happen that at some position it would be enough to get infinitely many numbers. This is what came to my mind when I looked at this position. So you may have, it may happen that you have finitely many alphabets for which you have a finite process, and infinitely many alphabets for which you have infinite process. So this is the third possible conjecture you can put between two conjectures you posted here. So probably this is my comment. And maybe second comment that on my experience with ternary square free words, I very strongly believe that the procedure for nonchalant words is infinite. I
Yes.
can bet anything for this is sure, but it can be tricky to prove. Yes, maybe not. If I have time, I will try to use some machinery I know. Yeah, but I'm sure that this one is true.
Okay. Thank you.
Would not be so sure for bigger alphabets, for the questions you put. But anyway, thank you very much for the talk. Yes.
Thank you for the comments. Interesting. Yes.
Are there any other questions? All right, well, if not,